So it is Thursday. It's the second lecture for Biology 105 this fall. And first couple of things. Number one, any questions on bookstore materials, getting registered, going to lab, anything like that? Any problems with shortages of materials?
I'm having problems doing the mastering AP. So
Okay, hold on, and I'll get to that in a second.
Okay.
Number two, I hope everyone got I'm looking at a couple of announcements here. An announcement about the walk-in tutoring schedule, and this is Monday, Tuesday, Wednesday, and Thursday. We've got Andrew or Janae. They are available for you. They're in room 249. That's the study room right across the hallway from the labs, and they are sitting there waiting for you to come in and ask questions. So please take advantage of that. It's a great place to go, and even during those hours, you can also go in there individually and not even speak with them, and that's where we have other resources. There are computers in there you can use. There's an overhead projector. There's a whiteboard. You can shine your PowerPoints on the screen and practice things. So as we get more into the course, and as you find yourself needing to do more repetitive labeling of structures and interaction with bones and muscles and things, you'll find that to be a very, very good place to hang out. Number three, my readiness test. That's separate from mastering, and there was a separate link and a separate course ID that I sent you even before classes started, and that is due, I think, by August 31st. It's an internal, for my own benefit, sort of a pre-test for your overall knowledge about anatomy and physiology. You will not be docked if you don't do well on that test, but I would ask that you go in there and just do your very best job on that, and that will give me some predictor and some information I'm trying to gather about where students' deficits are coming into this course so I can be aware of those. Number four, wherever I am, just an overall in mastering. Now, I think part of the confusion is I wrote up my syllabus before I realized that registering and mastering was easier through Blackboard. And so in the syllabus, I mention on the green syllabus, I mentions that you'll need to use this course code, MAP Macauley 9662, to get registered. In the end, that was a mistake, and on Tuesday I forgot to give this little commercial about this, and I apologize if this has caused any confusion for you. Instead of going through a website like this and going to this course code, it is far better and easier, and actually the only way to do it is simply to go into Blackboard and click on Mastering. Now, I can't replicate what you'll see the very first time, but when you click on Mastering A&P, the very top link here you'll click on that and it will bring you to a registration page. It'll ask you to set up a new account, put in your name, your username, your password, your email, and then you'll put in that 16-digit code that you got, the modified mastering code that came with your Martini textbook. If you've already signed up for the My Readiness test, you already signed up with a Pearson account. So if you've already done the My Readiness test, you'll go into I already have a Pearson account, and then you'll put in that 16-digit code, and it will automatically put you in this mastering course. You won't need a course ID. Okay, in fact, if you go the other way and try to get into this course, 9662, whatever this is, I don't think this course even exists because of the changes that I wasn't aware of when I printed this. Okay, so that may help clarify some things, but afterwards, those who are having trouble, let's come in here and we'll do it right after class. I'll have to log out, you log in, you go to Blackboard, and we'll try to go right in. Okay, so we'll try to get that hooked in. What else? Don't forget the next Monday and Tuesday we don't have classes, and so Wednesday of next week will be the first lab of the sequence, and everyone here has already been to lab, right? If anyone here did not go to lab Monday or Wednesday, then you need to take lab today and talk to me about making that up. So I think that's all my pre-announcements. Anything of concern that I haven't mentioned? Oh, one more thing. When you go on Blackboard as well, there'll be YouTube lecture links, and here you'll find the fall lecture. And I've already posted the links to YouTube, so the lecture that I captured on Tuesday is there for you on YouTube, as well as I captured one of my presentations that I gave in lab, the lab 1, just the PowerPoint portion. So those are viewable for you. Just kind of cut and paste that link into your browser, and you will be able to review the lecture at your convenience. So I think that you'll find that to be a very useful tool. I've also set up a discussion board, and this discussion board will allow you to ask any questions from Lab 1 or Lecture 1. I'll get in the habit of checking that out and responding either in class if it's something that I think I forgot to say or I need to clarify, or I'll respond to you individually if there's something, or just respond to the thread. So if you're studying and you come across something, it might be useful to email me a question, but I'm also, this is my first time playing with this discussion board, so I want to see how this works. So I encourage you, if there's some burning question, not something you need a response for in 5 minutes, but if there's something you just in general are not making sense of, please post it there. All of you also can respond to it. So if you know the answer, jump on in and respond to it, and I'll try to develop this whole discussion board idea. It's a useful tool. I just haven't used it myself in the past. So there might be a little bit of learning going on there, but I hope it'll be useful for you. And I'm also going to have the tutors checking this out as well, so that they can see and maybe respond to some of these questions as well. Okay, so last time we finished up chapter 1, and in lab you've already had a discussion on anatomical terms and directions and body cavities and serous membranes. You already have 2/3 of the first exam. The first exam is lecture 1, chapter 1, which we already did. It's the discussion we had in lab about body directions and terms, and it'll be chapter 2 on chemistry, which I'll be covering today, and a few leftover things, I'm sure, next Thursday, right? It'll be a week from now before we have the rest of chapter 2, which is why the first exam seems so far away, and yet it isn't, right? September seems so far away. But if you look at the syllabus, what does it tell you? It tells you that our first exam is on the 9th. It's going to cover chapters 1 and 2, and the atlas, and the material from lab 1, and vocab slides 1 through 16. Okay, so let's go to vocab. So let's go to the vocab right now and pick up. I believe I went through the first 5 slides with you last time, and let's get started. If there are any questions at all, let me know as I'm pulling up this presentation. Anything at all right now before I get started? Everything's feeling good? You're starting to get into the groove of the semester? Other classes are jiving well? Have you put all the exam dates on your master calendar? Lab exams and lecture exams. That way you've got one master calendar, if you will, for yourself. And I find that oftentimes many classes have the same sort of routine. So you may find there's a couple weeks from now, you may have a lot of exams in your other classes. Okay, so moving on with vocab, I'll go through about 5 or 6 more slides today. So before. So we've seen the antebrachium in class. Antepartum, before birth. Anti, against. So an anticoagulant would be a medication or a compound that prevents or goes against the clotting of blood. APO is separated from, and APS and APT, if you look, they mean fit or fasten. The example here is a word we'll become very familiar with, and that's synapse. When we get to the nervous system, we'll see where 2 cells come into close proximity. That's called a synapse. And you can see that there's an APS in the middle of that word, right? So syn means together, and aps to fit or to fasten. AR, if you have arrhythmia, you're without rhythm. So AR is a negating term, just like A and AN. Arche, the beginning of something or the origination of something. Menarche is the first menstruation, the beginning of the menstrual cycles in a woman's life. Arthro, joint. Arthritis, an inflammation of the joints. Itis means inflammation. So arthritis, inflammation of the joints. Atria, I've got a typo in here. This should be A-T-R-I, not A-R-T. So drop off that first R. And this is sort of like the word atrium. So the blood first enters into the heart, into the atria, or into one of the atriums. And your home or church, you may consider the entryway also the atrium. Airy, associated with, and if the term ends in ASE, it is almost always an enzyme. And we'll talk about enzymes a little bit later today, certainly by next Thursday. And for examples, in the term polymerase or kinase, you're not responsible for knowing what those particular enzymes do, but just know you see them ending in ase. It tells you that they're an enzyme. Asis and Asia, A condition or state of. Look at the term homeostasis. Right? We know that that means no matter how brutal the external environment is, that the body tries to maintain its internal systems in a regular area, or keeping things within a normal range. And so we see that asis at the end. So homeo means similar. Right? So homeostasis, keeping things within the body similar. Asthen, weakness. We'll see later that myo means muscle, so myasthenia would be a condition where the muscles are weak. Athero is fat. Yep.
Is there supposed to be an H in myos?
Let's see. Absolutely, thank you. Another typo. So in the example, myasthenia, there should be an H in there, just like the word. Thank you. Arthro, fat. Atherosclerosis, you've heard about this. This is a hardening of the arteries, which is oftentimes built up by a lipid or fatty blockage. Audio, hearing, that one's not unfamiliar. Ari, the outside of your ear, the flappy portion of your ear is called the auricle, and so referring to the ear. And auto means self. Baro, weight or pressure, barometer, right, measures pressure. People have bariatric surgery to help with weight loss. Beni, good or well. If you give a benediction, you're giving a good word. Benign, if you're told that you have a tumor and it's benign, that's also a really good word, isn't it, right? That's a good diagnosis. Bi, twice or double. Think bicuspid, the teeth with 2 points. And bio, here we are in a biology class. We're learning about life. And I'll go through 11 today. Blast. We'll see some cells. Osteoblasts, chondroblasts. These are all cells that make something, or something germinates or buds from them. So we'll see fibroblasts, lots of cells like that. Brachy, you know the brachium is the upper arm. And the biceps brachii, for example, the muscles of the upper arm. Brady means slow. If you have a slow heart rate, you would say to have bradycardia. And finally for today, bronch, like your bronchi, the air passages going down into your lungs. If you had an inflammation of those bronchi, you would have bronchitis. Again, how far are we going? We're going through 16. So I'll finish those through 0 next Thursday. And there's no reason why you can't go ahead and make up your note cards for all of these, A through 0 for the first exam. Again, this will be fill in the blank for the most part. I'll put 2 of these terms together and ask you what they mean. So just kind of take your note cards, know them individually, but then kind of just play around. Put those words together and ask yourself, okay, if you put those 2 together, if you put those 2 together, what would that mean? And play that game yourself, and you'll probably come up with the same combinations that I'll quiz you on the exam. Any questions on vocab? Okay, any questions on Chapter 1? Anything at all that we discussed in the Chapter 1 presentation? That was an introduction, wasn't it? We kind of went over some themes, some ideas. We defined anatomy and physiology. We looked at that atom-to-atom continuum. And we discussed how Aristotle said that all complex things are made up of less complex structures. And I described to you how ATOM, atom, molecules, macromolecules. In fact, let's go through that hierarchy right now. So if I'm talking about the atomic level, atoms, right, ATOM, make what? Combine to make molecules. Those smaller molecules can combine to make larger molecules referred to as macromolecules. Macromolecules include things like what? What are some examples of? Proteins. I heard proteins. What else would be a macromolecule? On your food label, what are you reading? Carbohydrates, proteins, lipids or fats, and finally the one that we don't think about, but we certainly consume, nucleic acids. So DNA and RNA. We eat it, right? It just doesn't have any nutritional value. So those are the 4 major macromolecule groups. And then those macromolecules, like proteins and lipids and carbohydrates, are the building blocks for what? What's our next level? Not yet, not the cell. The building blocks of the cell would be the organelles. The organelles include things like what? Give me a couple of examples of organelles. Am I hearing Golgi and endoplasmic reticulum? And we'll go through those things in chapter 3. Then the organelles are the major building blocks for cells, right? Cells being the most fundamental living thing. There are over 75 trillion cells in your own body. There are over 250 different kinds of cells in your body. And those cells are then the building blocks for tissues. 4 types of tissues. Connective, epithelial, muscle, and nervous, right? Those are the 4 classes of tissues. We'll get to know them well and know what they look like under the microscope. Those tissues are now the building blocks for organs, right? The entire organ, like a heart, liver, kidney, spleen. And then those organs combine in different combinations to make the 11 organ systems, 12 if you count both reproductive systems. And those 11 systems now combine to make you and me the organism. Okay, so that's our hierarchy from atom to atom. Know that hierarchy. And then we also talked about the different organ systems. You saw those in lab. You saw them in lecture. Clearly, you need to know the organ systems, be able to recognize them, know their organs, and know their functions. Not to write out an exhaustive list, but on a multiple choice type test, be able to identify what does not belong, which one does not match up, or perhaps if I gave you a list of functions, you would recognize that those functions belong to whatever system, okay? So that's how you'll be quizzed on that kind of material. And then that pretty much brings us up to, there was one other key term from last time, and that was homeostasis. And what is that? Homeostasis is the process that does what? Keeps everything internally as constant, or at least within a workable range as possible. And what was the major mechanism to maintaining maintaining homeostasis? Negative feedback, right? The idea that as the temperature rises, your air conditioner comes on. As your temperature lowers, your heater comes on. And in our body, the air conditioner and those heaters would be like hormones or other mechanisms that would knock things back toward what we call a set point. So you set your thermostat at 75 degrees. Your body also sort of has a set point and is trying to keep things around 75 degrees, if you will, or if your body temperature at 98.6, and if it starts going high or low, there are mechanisms in place that will kick it back toward its expected value. Okay, so that brings us up to chapter 2. Anything else in that conversation that needs to be clarified? Okay. Any questions on lab? Directional terms, body cavities, serous membranes, anything in there that you can think of that's giving you any trouble? It needs to be said again. Okay, chapter 2. Chapter 2 is a chemistry chapter. I'm not going to make chemists out of you. If you've had chemistry in the past, you might feel like this is a little bit of a snooze fest because I'm going over some very basic ideas. But if in fact our body is made up of organs and cells and tissues and organelles, we need to understand the basic building blocks of our overall body. So we will start back at the atom and molecular level, and that'll be the focus of chapter 2. Actually, not only will it be atoms, molecules, but also macromolecules. So we'll mention the macromolecules also in chapter 2. Then when chapter 3 comes along, which is not going to be on this test, but on the second test, by that time we'll be talking about cells and tissues. And then eventually, it won't be very long, but eventually we'll get up to what you think you signed up for, and that is anatomy, right? It's like, where's the anatomy? I want to learn about bones and muscles. We'll get there. Okay. So let's start back. So I'm trying to argue that we need to learn a little bit about chemistry because we are in fact made up of those molecules. There's a whole area of study called biochemistry, and our overall metabolism certainly depends upon understanding the molecules that are a part of you and me. Just a introductory slide on probably some physical science definitions. So matter is anything that occupies space and has mass. I know that's a definition that you learned somewhere back in middle school, early high school. That seems to be one of those definitions that everyone has had to learn at some point. That matter is anything that occupies space and has mass. So now the question is, what's mass? Well, mass is the amount of stuff, the amount of matter in an object. It almost seems circular in a way. Okay, now, when you hear about mass, if you're in a chemistry or a lab, they'll talk about mass, right? What's the mass of something? We don't walk around saying what's the mass of something. We instead walk around and saying how much does it weigh? They're not exactly the same, but in our everyday experience, we talk about how much something weighs, right? Bring it to the scale and how much does it weigh. We are also measuring its mass. The difference is that weight is based upon gravitational force. So when I step on my bathroom scale in the morning and I look at the number, and after I wipe away the tears, right, I realize what's going on. It's the Earth's gravitational pull pulling me down onto a series of weights and springs that are measuring my weight. What if I took my bathroom scale to Kilimanjaro? Would I weigh the same? No, right? I'm going to weigh less. Why? Because at a high altitude, there's less gravitational pull. And if I took my bathroom scale and went to the moon, I'm really going to like the number, right? Because there's no gravity, so I'm going to weigh essentially nothing. But if I took my mirror from my bathroom with me to the moon and I look in the mirror, what am I going to see? Same old thing. So my mass is the space that I take up and all the matter that makes me up, all my atoms, but my weight is dependent upon gravity. So we use them every day as the same term, but in fact they're quite different. So what is it that makes us up? We're made up of atoms. And if I had a hunk of gold or a hunk of pure carbon or a hunk of pure aluminum, what is a hunk of pure aluminum made up of? Right? That's one of the elements, aluminum. And if I could look at it at the atomic level, I would realize that that hunk of pure aluminum is made up of all aluminum atoms, right? Or gold or silver or you name it, those elements are made up of individual atoms. On the Earth, there are about 112 elements that naturally occur on our planet. There are a few more on the periodic table. These are mostly man-made, and they have, they're man-made. They're not naturally occurring atoms. Of those 112 elements, only about 20 of them are required for life. And these are the 20 that you'll see on your vitamin bottle. So you look on your vitamin and you'll see under the ingredients or somewhere within the ingredients, you'll see magnesium and molybdenum and you'll see cesium and you'll see some of these smaller or these less important, or not, shouldn't say less important, important atoms or elements that are important for our life. Of all of our body, about 96% of our body is made up of just 4 elements: carbon, oxygen, hydrogen, and nitrogen. So those are the 4 that make up the vast majority of our body. In fact, I've heard it said that if we turned our body into a junkyard and just kind of sold off our elements, we're worth about $6 on the black market, right? So we're not worth a whole lot when it comes to our atomic makeup. So atoms are the basic unit of matter. Well, now the question comes, well, what in the world is an atom? So we're going to break it down just a little bit more to understand what an atom is. And once we break this down, I think you'll appreciate why we're having to look at this. An atom consists of a nucleus. Now, I'm a biology guy, so when I hear the word nucleus, the first thing that comes to my mind is the place within a cell where the DNA is found, right? In a typical eukaryotic cell. That's what first comes to my mind, but I have to remember that nucleus has other meanings as well. So a nucleus is the very center of an atom, and that nucleus will be surrounded by some electrons. So in this cartoon, the blue is the entire atom, and don't get caught thinking this is a 2-dimensional flat circle. This is a 3-dimensional sphere. Okay, and that's the atom. And the red circle, the very red center, represents the nucleus. The nucleus is very small compared to the overall size of the atom. In fact, I've had it been told that if you were in a large football stadium, so I'm a Florida Gator guy, so I'm thinking about Florida Field, but if you're at the Big House, Michigan, or whatever, and if someone could dangle something in the size of a pea to a golf ball or something in that scale over the 50-yard line from on high, the stadium, all of the seats of the stadium, all the space of the stadium would represent the atomic size, and that little golf ball or orange or pea or whatever that scale is hanging over the 50-yard line would represent the size of the nucleus. So the nucleus is a very, very small, compacted portion of the overall atom. Inside the nucleus, there are particles called protons, and they're called protons because they are positively charged. And those protons, right, there are protons inside the nucleus, and they are abbreviated P+, because they are positively charged. And there are also within the nucleus neutrons. They are neutral in charge, and they are sometimes abbreviated N superscript 0. Floating outside around the nucleus, out in this blue cloud, would be some electrons. Those electrons are negatively charged, so they're going to be abbreviated E negative, E minus. You'll see where we're going here in a second. So here we go. So protons in the nucleus, positively charged, and this is what basically defines an atom. A hydrogen atom always has one proton. If you change the number of protons, you change the atom. Carbon always has 6 protons. So every single carbon atom will always have 6 protons. If I change it to 7, it's nitrogen, and you don't have to know all that. Also squeezed into that small nucleus are other particles called neutrons. Again, they're neutral in charge. How much, and I'm going to use that word weigh just to get us to think about it, but how much an atom weighs, or what the atomic mass is actually, you just basically add up the sum of the masses of the protons and the neutrons. So carbon always has 6 protons and typically also has 6 neutrons, and each of these, both protons and neutrons, have what we call a mass of 1. And again, I'm not going to get into all of this, but we would say that a carbon atom therefore has a mass of 12. Okay, 12. Now outside of the nucleus, out in the orbit, out in that blue cloud, is where the electrons hang out. Now the electrons are negatively charged, but they weigh so little that we really don't even include them in the mass. So they're sort of just this extra non-weight-bearing, non-mass structures with a negative charge sitting outside in that cloud. So if this were back at the football stadium, the protons and the neutrons would be squeezed into that little golf ball hanging over the 50-yard line, and the electrons could be sitting anywhere. They could be anywhere on the field or anywhere out in the crowd. So taking a look at this cartoon of some atoms. On the upper left, that's a cartoon representation of a hydrogen atom. Hydrogen always has 1 proton, so you can see the 1 proton, the 1 P+, and it happens to be that hydrogen usually has 1 electron around the outside. Carbon's in the middle. That cartoon shows a nucleus. I know it's hard to read. It says in there that there are 6 protons and 6 neutrons. So that means that the mass, we've already said, is 12, right? And outside in the cloud, there would also be 6 electrons. On the far right, that's an oxygen atom. And oxygen is the 8th element. So it has in its nucleus 8 protons, also typically 8 neutrons and 8 electrons. If you've had chemistry, you know it can be a little bit more complicated than this, but we're not going to go much deeper than this in trying to understand basic atomic structure. Let's look at this first statement. The atomic number equals the number of protons. So like I said, hydrogen always has one proton, so the atomic number of hydrogen is 1. Carbon always has 6 protons, so the atomic number of carbon is 6. Oxygen's always 8. So let's fill this blank in. Since electrons are negative, and I'm telling you now that all atoms are electrically neutral, right? That is that they have an equally balance of positive and negative charges. That means that the atomic number is what as compared to the number of electrons? The same, right? So fill the same in there, or equal to. So the atomic number is going to be equal to or the same as the number of electrons. Because if I gave you a carbon atom, right, atoms are going to be neutral. And there's going to be as many positive charges as there are negative charges. So what makes one atom different from another? What makes the atoms of one element different from another? And it comes down to the protons. Okay, so again, carbon always has 6. Oxygen always has 8. If you change the number of protons, you are changing fundamentally the identity of that atom. And this is what alchemists tried to do for centuries, right? We've been trying to make silver change into gold, or make lead change into gold. And we realized that, you know, it's not possible to do in the way that it was hoped. Now, what about neutrons? Neutrons actually vary in their number. So I always, remember, neutrons have no charge. They're not contributing to the charge, but they do contribute to the mass. And there's a variable number of neutrons possible in different atoms. And we call these varying versions isotopes. So an isotope is something that's used a lot in medicine. Isotopes are usually unstable. And when you hear about an unstable element or an unstable atom, we're referring to radioactivity. So it breaks down, and when it breaks down, it emits energy. Right, so radioactivity is dangerous in too much, right? Too much radiation can damage us because the elements are breaking down, and as they break down, they release harmful energy particles that can damage our cells. But in medicine, remember I mentioned the PET scan? And the PET scan was the injection of a radioactive glucose-like molecule, and we watch that radioactivity spread throughout the body, and where a lot of that radioactivity accumulates tells us what? That the cells there are very, very active. Whereas if there's no glucose accumulating, then we know that there's been tissue damage to that particular cell or that particular area of the brain or the heart. So we can use radioactivity in marvelous ways in medicine, in imaging techniques. So the protons, the number of protons defines the element. The number of neutrons can vary, and those variations are called isotopes. Just to give you an idea of this, so there are 3 different isotopes of hydrogen. When you hear the word isotope, just put the word in your head, variations. 3 variations of hydrogen. And I told you that hydrogen always has 1 proton. So the number of protons is non-negotiable. Hydrogen will always have 1 proton. The variation here is going to be in the number of neutrons. So the most common type of hydrogen is called H1, and that 1 refers to its mass, and that mass comes from the one and only proton that's found in its nucleus. There are no neutrons. Another variation or version of hydrogen is H2. It's called deuterium. Well, it has a mass of 2. Where must that second mass unit come from? There's only 1 proton. There has to be only 1 proton, so there must also be another 1 neutron hitching a ride in this nucleus. And then there's tritium, 3, tri, and it has a mass of 3. Well, it only has 1 proton, it's hydrogen, so the rest of the mass must be coming from a pair of neutrons that reside in the nucleus. Isotopes of carbon. You've heard of radiolabeling, carbon dating perhaps, and that is based upon carbon-14. So carbon-12 is your basic type of carbon. I've already kind of shown you carbon-12. Carbon-12 is the basic boring carbon that has 12 protons and 12 neutrons. It has a total mass of 12. but there is a variation, an isotope of carbon called carbon-14. And carbon-14, the extra 2 mass units come from an additional 2 neutrons. The problem is, or the issue is that those isotopes are unstable. So they break down at a predictable rate, and with that breakdown rate, we're able to age things because we're carbon-based life forms, aren't we? So everything in our universe that's living is composed of carbon, and so we can use this as a measure of age in artifacts. So what do we know? Protons, non-negotiable, define the element or the atom, and neutrons vary, and those variations are called isotopes, and those isotopes are unstable. The third guy we need to keep track of are the electrons. And actually, electrons, for our discussion, the electrons are going to be the most important thing. Because when atoms combine or break apart, there's always going to be an interaction with the electrons. Every chemical reaction that occurs in our body is going to involve the breaking of, or the separation of, or the combining of atoms. Okay? And the electrons are going to sort of dictate what atoms can and what atoms cannot combine in our body to make different molecules. Let me describe this to you. So outside the nucleus, out in that blue haze, in that cartoon, out in that shell, or out in that orbital area, there are what we call shells. Now, this is sort of like layers of a pearl, or layers of an onion. So the electrons aren't just hanging out anywhere, right? The electrons are defined. So the electrons have a seating assignment, if you will, out in the stadium. And each electron has an assigned area, and each area has a limit as to the number of electrons that it can hold. And one of the rules in chemistry is that an element wants to have a full outer shell of electrons. If the outer shell of electrons is full, then that atom is said to be stable. Okay, that molecule is said to be stable. So let me describe this with carbon. Carbon is the 6th element. It has an atomic number of 6. Therefore, how many protons does it have? 6. Right? You're going to hear enough about carbon. You're going to know that carbon always has 6. And if you're digging up carbon out of your backyard, how many electrons would it have? Remember, atoms are always neutral in charge, so there'd be an equal number of electrons. So there'd be 6 protons, and there would be 6 electrons. So let's draw this out in a schematic. So this little green circle represents the nucleus. And in the nucleus, we just said there'd be 6 protons. This is your basic carbon-12. So carbon-12, if you look back on that isotope page, carbon-12 would have 6 protons and 6 neutrons, wouldn't it, in its nucleus. So there they are in the nucleus. And then I told you that there are around the nucleus, there are shells. Now, they're not circles like this. They're going to be spherical shells, imagine like an onion peel, if you will. And I'm going to tell you that the first shell, the shell closest to the nucleus on the inside, is rather small. And it only has room for 2 electrons. So there are going to be 2 E negatives, 2 electrons hanging out in that first shell. Once there are 2 electrons there, that's all it can hold. Now, how many electrons does carbon have? 6, right? So we put 2 in their place. We've got to still seat 4 more electrons. And now we're going to go to a second shell around the outside. It's a more external, superficial layer. And there will be 1, 2, 3, 4 electrons. Okay. Now that second shell, however, can hold 8. So it's not full, right? There's room for 4 more electrons. And I'm just telling you, this is a fact, right? There's no way of knowing that. I'm just telling you, the first shell holds 2, the second shell holds only 8 electrons. So from the axiom that I told you, would carbon be happy? Would it be stable? No, right? It would want what? It would want that outer shell to have all 8. Or if we got rid of 4, if you have an empty shell, it's sort of like it gets erased. It's not even there. So if we lost 4 electrons, what would happen? Then we would only be dealing with that inner shell. It would have 2 electrons, and it too would be happy, stable, or full. Okay, so carbon, because it can gain 4 or lose 4 electrons, becomes the basic building block. We're said to be carbon-based life forms, right? All of our biochemistry is based upon carbon. It is the key building block for the molecules that give us life. So carbohydrates, nucleic acids, lipids, proteins, all those macromolecules depend upon heavily the presence of carbon. So as our body is doing its biochemistry, as we take in energy, as we eat, and our body breaks down those nutrients, what's really happening is that electrons are being gained or lost, moved around, and all of these chemical reactions are going to fundamentally be dictated by the electrons. Now, there's a couple different ways that these electrons can behave. We're going to refer to chemical bonding. How is it that different atoms bond together or come together or react together? The first way is that those outer electrons, just the ones on the outside, those outer electrons can either be transferred, that is taken away, right? Taken away or gathered, or they can be shared. That is that they kind of hang out there and they're sharing between 2 different atoms. So we're going to look at these 2 different types of chemical bondings. One is called ionic, the other covalent. We'll start with ionic. Ionic bonds. It's involving ions. I'll get to that word in a moment. When I hear ionic bonds, though, for some reason, I still go back to a lesson I learned in high school about, I remember it was in a humanities class, and I remember learning about ionic columns. Bear with me, but this is what comes to my mind. So somewhere in my Western humanities or civilization course, I remember the Greek architecture and these ionic and Corinthian columns. So these ionic columns that make up the Parthenon, etc. And then I think to myself, oh, the Greeks who built these ionic columns were rather a warring people, right? Historically, they were a conquering people. And they were gaining battlegrounds. And so I just have this word picture in my head that ionic bonds involve the capturing, the warring, the taking over of electrons. So in ionic bonds, the electrons are either completely gained, conquering, or completely lost. They lost the battle. And the molecule that we're going to study for ionic bonds is sodium chloride. You know sodium chloride. It's just good old table salt. And what you have is the coming together of a sodium atom and a chloride atom, or chlorine atom. And it's interesting. Sodium's a metal, right? Sodium's a metal, and chlorine, in its natural state, is a gas. So you have this metal and this gas that come together to make something kind of tasty. Now let's take a look at how this works at the atomic level. The upper left, the pink, that represents a sodium atom. Now I'm telling you that sodium is the 11th element. So therefore it has 11 protons in its nucleus. Well, if it has 11 protons and atoms are neutral, then it must also have how many electrons? 11. Where would those 11 electrons be? Okay, so let's think about this. So where would those 11 electrons be? So here is my nucleus. This is sodium. So what's going to be in my nucleus? Oh, I said 11, right? My bad. So we're going to have 11 protons. Let's not worry about the neutrons right now. They're not going to matter. So 11 protons in the nucleus. And then there's going to be a shell. That first shell can hold how many electrons? 2. So I'll put an E minus and an E minus. And it's full. That's it. There's still how many more electrons to find a home for? 9 more, right? The next shell can hold how many? I told you it can hold 8. So I'm just going to make it really easy. Put 8 electrons out there in that second shell. But I still have how many more electrons? 1. And that one leftover electron is going to have to go to the next seating area. It's going to have to go out to the third, and there's going to be one lonely electron out here. Now, in chemistry, I'm telling you that the atom wants to have an outer full shell. So what do you think sodium would like to do? Get rid of this guy. And if we get rid of that electron, now what do we have? A full outer second shell. So that's exactly what sodium does. Sodium, up here in the upper corner, has, you can see the 11 electrons, okay? 11 protons and 11 electrons. Now the other atom that's involved here is chlorine. Now chlorine is the 17th element. So it has to find room for its 17 electrons. So where are they going to be? Where are those going to be? Any guess? So we're going to have, I'm just going to make this simple. So 17 protons in the nucleus, right? And then first level, how many? 2. Second level? 8. Third level? 7. Okay, I'm going to tell you for the purposes of this class that that outer shell also holds 8. Okay, just for what we're doing here. If you've taken chemistry, you know I'm kind of bending the rules here a little bit. But for what we're doing here, this makes sense. So the third shell also holds 8. So what would chlorine want to do? Gain 1. Where's it going to get it from? Sodium. So this is a perfect pairing, right? It turns out that it's the electrons in the outer shell that dictate how, when, or if atoms will combine. So sodium is trying to desperately get rid of 1. Chlorine would like nothing more than to gain 1. And this is why these two atoms can combine. So what we see here is that in this ionic bond, that sodium loses an electron. So it completely loses an electron. Okay? Now, as it loses its electron, now what do we have? Now, how many electrons are there? 10. Right? But how many protons are still in the nucleus? 11. It's still sodium. It has to have 11 protons. So what now becomes the charge? Overall, I have 11 positive protons in the nucleus, but I've lost an electron. I only have 10 negative electrons left. So overall, what's the charge of sodium? Yep. Plus, or plus 1. Now what happened to chlorine? Chlorine gained a negative charge, didn't it? There was a complete transfer of electrons. So chlorine had 17 protons in the nucleus. It just gained an 18th electron. It has now more negative charges than positive, so chlorine has a charge of -1, or just minus. This form, Na plus or Cl minus, are called ions. Okay, so in an ionic bond, you're creating ions that combine, and there's a complete transferring of electrons, a giving or a taking away of the electrons. And what you see now is this tight little shell. So a salt crystal, we all know what a salt crystal looks like, right? Under the microscope, it would look like this. From an atomic level, I mean, things we can't even imagine how small they are, but you would end up with this little arrangement of sodium and chlorine atoms all tightly compacted together. And it's pretty stable, right? Because sodium and chloride ions have an outer shell that's full. They've gained or lost an electron to make them happy. So that's ionic bonds. Now you're going to get a chance to practice this, if you will. Another reason why exam 2 is a little bit far out, not only because of the holiday, but lab number 2 is all about chemistry. Not all about, but has a chemistry component to it. And as you're doing your pre-lab for lab number 2, a part of that asks you to walk through this same story with ionic bonds and sodium chloride and moving the electrons around and understanding the number of protons. So as you do pre-lab number 2, you are really studying also for this portion if this isn't making sense to you. It'll also describe to you covalent bonds. Now my word picture for covalent is love. If you take the word covalent and you pull it apart, you'll find in there L-O-V-E. So covalent bonds are when the electrons are shared, right? We love each other, we share. Okay? My kids love each other, they share sometimes, right? So the electrons are being shared. And here there isn't a takeover, right? This isn't a hostile takeover electrons. The electrons are instead shared. There's 2 different ways that electrons do this sharing. The first one, the example is going to be hexane. Hexane is this molecule here. What it has is there are 6 carbon molecules, right? You see 6 carbons here in the chain, and each carbon is surrounded by hydrogens, the H's. And we'll use hexane as an example. Let me just move ahead and I'll come back and explain this to you. But here the electrons are being shared. 2 different kinds of covalent bonds. One where the electrons are being shared equally and one where they're not being shared equally. In hexane, it turns out all the electrons are being shared equally. In water, which is our example for a not equal shared example, the electrons are not shared, and I'll start here because I think it's easier to talk about water. Water is an amazing molecule. It is H2O, we know that. It's 2 hydrogens attached to an oxygen. And we see here in this little Mickey Mouse cartoon, the oxygen and the 2 hydrogens. You see a line between them. That line represents a covalent bond. So that line, that solid line you're seeing between the oxygen and the hydrogen tells us what? That the electrons are being shared, right? That's an a covalent bond, and the electrons are being shared between the oxygen and the hydrogen. But they're not being shared equally, right? So this is kind of like my kids, right? I mean, they love each other, but they're not exactly sharing things equally. And that always creates a sort of a tug-of-war situation within the family dynamics. Same true in water. This little scale over here on the side tells us that oxygen is more pink. So oxygen is more negatively charged. You can't see that well. Oxygen is more negatively charged, and the hydrogens have more of a positive charge about them. So even though the electrons are being shared, they're not equally sharing, and that sets up what's called polarity. Polarity. This is a polar bond. When you hear the word polar, what comes to mind? White fluffy bears? Maybe? But what else? Polar. The Earth has a north and a south pole. Magnets have poles, right? Polarity is the idea that there's a positive and a negative. There's something pulling, separating. There's polarity in water. The electrons are shared, but they're not shared equally. And what that does is it makes water partially negative and partially positive. This is also the characteristic that makes water such a great solvent. That is, so many things dissolve in water because water is partially positive and partially negative. Right? So it attracts different molecules, and it acts as a great way of dissolving away different molecules. Now back to the hexane. In the hexane, that is a non-polar covalent bond. Let's break it out. Covalent, the electrons are being shared. Non-polar because there is absolutely equal sharing. Right? There is no negative and positive polarity. So all the electrons are being shared equally. There's no yanking, and therefore hexane, this molecule on the previous page, would have no negative or positive charge associated with it. It's truly neutral, non-polar. Now there's one more kind of bond that I want to introduce to you, and that is hydrogen bonds. Now these are not covalent bonds. So this is not ionic nor covalent. This is a different, completely different kind of chemical bond. And each of these little blue L-looking shaped things here represents a water molecule. The red sphere is an oxygen. The little bluish gray guys are hydrogens. And it even shows you on here that the hydrogens have a little bit of a positive charge. Right? You see the positive sign, and the oxygens have a little bit of a negative sign. So that means that when you have a beaker of water, that the water molecules, just like little magnets, are being attracted toward each other. That attraction is the hydrogen bond, and it's shown here as a dotted line. See the dotted line? Not a solid line. The solid line was a covalent bond. The dotted line here, the dotted line represents the hydrogen bond. So what you have now is a weak, very weak affinity, attraction of the positively charged hydrogen with the negatively charged oxygen between different water molecules. So this is a weak attraction between different water molecules. And you've all probably experienced hydrogen bonds. You've seen the evidence that water sort of sticks to itself. You've seen this when you fill a glass of water up to the very, very top. And if you look at a glass, you'll see the water will actually almost go over the top and almost dome a little bit. Right? The water molecules are sort of sticking to themselves before they fall over the glass. Or you've seen insects walk on water. Right? And the reason they can walk on water is that there's enough stickiness, if you will, between the water molecules that these light animals, insects, can walk on the water. And you've also experienced a belly flop, right? And you realize that, yeah, you can jump into water, you can stick your finger into water, but man, if you're high enough and you hit that water flat enough, boom, you suddenly understand the collective energy that has been pushed back against you when you hit that water on a flat surface. You recognize that all those hydrogen bonds, while each one is very weak, collectively can create quite a turmoil, right? Which is why, I forget the numbers, but I think, I always forget this. Is it over 30 feet or over 60 feet? If you jump off a bridge or into water, you're likely not going to survive because the hydrogen bonding energy is so strong that it will break your bones, right, upon entry and kill you. And I forget the number, but something hideous, some horrible thought. But if you jump into water from a high enough place, it can almost be an automatic death sentence because of these hydrogen bonds. Any thoughts about hydrogen bonds, covalent bonds, ionic bonds? Again, you'll get to read through this, kind of walk through this worksheet idea in your pre-lab for lab number 2. If you've had chemistry, you're kicking back and saying, I got this, I'm okay with this. You'll want to review it, you'll want to do your pre-lab. If what I'm saying to you is brand new and you're like, whoa, I don't get this, you'll definitely want to spend a few extra minutes looking through chapter 2 of your textbook on the chemistry. Read through the visual textbook, it's very, very nice. And then you'll want to spend some quality time also in your Amerman manual in unit number 2. So now we know a little bit more about atoms. We know they have protons, electrons, neutrons. We understand that the electrons are sort of running the show when it comes to atoms combining in chemical reactions. So a molecule then is when atoms combine, right? So H2O, the hydrogens and the oxygens come together, the electrons are being shared unequally, and that allows us now to have a molecule. There are other molecules, C6H12O6. This one on the bottom, that's glucose, right? So C6H12O6, that's glucose, and glucose is a sugar molecule. And what does that tell us? That 6 carbons, 12 hydrogens, and 6 oxygens have combined in a unique way, and that their electrons are allowing them to combine in this unique way to give us the molecule of glucose. And every molecule in your body also is a combination of atoms which have come together in a unique way, and it's the electrons that run the show. It really is. It's these negative electrons and these outer shells that dictate whether or not atoms of a particular type are able to combine together. How are we doing? Any questions? Okay. What happens when you put salt into water? You sprinkle some salt into water. What happens? The salt dissolves, right? We've all experienced this. There's another word I want you to use rather than dissolve, and that is it dissociates. So when you pour salt into a beaker of water, it will dissociate. That is, it will dissolve, right? I mean, that's okay. What's happening is that there's a separation of the ions. Now, what is it that's going to cause sodium chloride crystals to dissociate in water? What do we know about water? Water is partially negative and partially positive. What do we know about sodium chloride? It's really positively charged sodium ions in connection with negatively charged chlorine ions. And so just like a series of little magnets, when you put sodium chloride into water, you've got all these negative and positive interactions, which are now going to cause the dissociation, the separation, the dissolving of the sodium. So on the bottom, there's our Mickey Mouse again. That's our water, right? You have the two blue hydrogens and the big red oxygen. Remember that the hydrogens are more positively charged, the oxygen is more negatively charged. So if I take a crystal of salt, that's one big crystal, isn't it, right? But take a crystal of salt and put it into a beaker of water, and this is my cartoon of the salt crystal. Again, remember, it's negatively charged chlorines and positively charged sodiums all bound together into a salt crystal. But look what happens when you put that salt crystal in water. Up here is sodium. The sodium gets surrounded, right? The positive charge of the sodium, it dissociates, it separates, and it gets surrounded by the water molecules. Look at the arrangement of those water molecules. What's being attracted toward the positively charged sodium? The negatively charged oxygen. Okay? So it makes like a sphere around the sodium. Now look at the chlorine on the bottom. Look what happened to the water molecules. They flipped, didn't they? Now you've got the negatively charged chlorine, and what's being attracted to it? The Mickey Mouse ears, right? The little positively charged hydrogens are now being attracted to it. Okay, so we pour salt into a beaker, and it dissolves, right? It dissociates. But what happens as you continue to pour salt into that beaker? At some point, what happens? It just stays there. It no longer dissolves or dissociates. But you want more of it to dissociate, so what will you do? You could add more water, and let's say right now I couldn't do that, or that's one option. What else could I do besides adding more water? Stir it. One more thing I could do. Heat it. Okay, so what does stirring and heating both do? Shakes around the water and the sodium chloride molecules, and what is it doing as it shakes around? Heating or stirring creates new arrangements and allows more water molecules to surround more sodium chloride ions, and you increase the dissolving ability, right? You increase the dissociation. And at some point, however, no matter how much stirring or heating you do, you reach a point of saturation. There's no way you can put more salt into that water. You could add more water, right? And then what's that doing? Again, creating more opportunities for dissociation. Okay, so add more water, heat it, stir it. We've all experienced this. You just never sat there and thought, oh, what's happening? Right? What's happening here? That's true not only of sodium chloride, but any molecule that's traveling through your blood, right, is surrounded by water molecules, and basically those molecules become dissolved or dissociated in the water. So we've looked at electrons. We understand that they dictate the ionic and covalent bonding, and we recognize that those negative and positive interactions are key to understanding our biochemistry. Now, there's different kinds of chemical reactions. There are synthesis reactions. That is, we're synthesizing something. We're combining atoms to make something. So you could imagine a simple equation like A plus B creates AB, some new compound, some new molecule. The arrow in chemistry that arrow represents a chemical reaction. And a chemical reaction always involves the rearranging of electrons. So when A and B combine to make this new molecule AB, you better believe that there have been interactions of electrons and there have been new chemical bonds, ionic or covalent, created in making this molecule. In your overall body functions, we might refer to this as an anabolic reaction. Let me change that word to anabolic, or your overall anabolism. Oops. Sorry, let me get it back here. So anabolism is all of the reactions in your body that build something. So we would say that this is an anabolic reaction. Now, where have you heard about anabolic things? Right? Where have you heard that word before, anabolic? Steroids, right? We hear about it all the time, right? So anabolic steroids are molecules, medications that people inject into them to do what? Build more muscle. So when you hear the word anabolic, just think anabolic steroids, think the building of muscle, and you'll have it. So anabolic reactions are a generic term for all reactions that cause the building up of molecules in your body. Now, you can appreciate that if you're going to build something, it's going to require some energy. It's going to require some input of energy when you build a house or when you build molecules. It's going to require energy. And in biology, that energy is almost always in the form of a molecule called ATP. So whenever you see the word energy in biology, especially in this course, it's always going to be this thing called ATP, and we'll come back to that, if not today, on Thursday of next week. Now, not only are there synthesis reactions, but you also have a lot of decomposition reactions going on in your body. That is the breaking down of things. So now you take that AB molecule and you chemically break it down to its components, that is A plus B, right? So we see the arrow, again, referring to a chemical reaction, a changing of the electrical bonds, and these reactions would be called catabolic. Catabolic. Vocab, not today, but the vocab I'll share with you next Thursday, one of the prefixes is catabol, and it means breakdown. Right, so catabolic reactions are reactions where things are being broken down or decomposed. And the opposite is true here. Typically, catabolic reactions give us energy. So it takes energy to build things, but as things are decomposed, we gain energy out of it. This is why when you eat a Snickers bar, you take in energy, right? You take in glucose molecules and other proteins, and what does your body do with it? Breaks down those sugar and protein molecules to give you energy, right? So when you're eating, your metabolism, your overall nutrition, the basis of your nutrition is that you're taking in large molecules, your body is breaking them down. As it breaks it down, energy is released, and out of it we get the energy. Our body eventually will make ATP from all that and energize all of our metabolism, the energy or the reactions of our body. Now, some reactions are reversible. I won't go into that in this course, but you'll see down here that there's a double arrow, both to the right and to the left, telling us that these reactions can go either way, to the left or to the right. Now, the other thing that's missing here, and I'll come back to it a little bit later, but in our bodies, almost every time where there's a chemical reaction, where there's an arrow, there's almost always an enzyme involved. I just want to say that now. I'll come back to enzymes later. But enzymes are biological catalysts. They are proteins that are going to facilitate or speed up a chemical reaction. And most of the chemical reactions in our body absolutely require a specific enzyme. So this one's small, and I'll come back and break this down in a bigger picture in a moment. what I want you to appreciate on this slide is this. The green hexagons across the top. Each of those green hexagons represents a single sugar molecule. And what this is showing you is that one single sugar molecule called a monosaccharide, mono one sugar, can combine plus, there should be a plus sign right there, one sugar can add to another sugar, so one monosaccharide plus another monosaccharide can undergo a chemical reaction, there's our arrow, to form a disaccharide. And a disaccharide is where two sugar molecules are connected by a chemical bond. Okay? So that would be what? If I'm going from one monosaccharide plus another monosaccharide and I'm building a disaccharide, what kind of reaction is that? I could call that a synthesis reaction, or I could also call that an anabolic reaction, right? It's an anabolic or a synthesis reaction. I am building something larger, and for that reaction to occur, it would require energy. It doesn't show that here necessarily, but there's going to be energy necessary to build this molecule up. And this arrow, again, is a chemical reaction, and there would be an enzyme that would do this job, right? There would be an enzyme, it's not shown here, but there would be an enzyme that would facilitate this reaction. And then look what you also get out of this. Water. Right, so as your body is building molecules, you get water as a result. Kind of a cool thing. Now this reaction, notice there's a double arrow here. So what does that tell me? That not only can it go from the left to the right, but there's another possibility for this to go from the right to the left. If we went from right to left, if I go this way, and I take a disaccharide and I break it down into two monosaccharides, what kind of reaction is that? Decomposition or catabolic, right? So a decomposition or a catabolic reaction where I'm breaking it down, and while it doesn't show it here, what else am I getting out of that? Energy, right? And what would be required for me to do a catabolic reaction? Water, right? So water is gained when we make things, but water is necessary to break these molecules down. Now across the top, those are sugars. Across the bottom, it's the same exact story in making proteins. And the middle is basically the same exact story in the making of some of your lipids. So this is sort of the same thing over and over in the breaking down and the synthesis of your biomolecules. I've mentioned energy, that it takes energy to do some of these reactions, and that sometimes you get energy out of some of these reactions. So let me just show you three different kinds of energy. First is potential energy. Potential energy, I think of, it's the energy that's stored in a molecule. It's not doing anything at the time, but it has the potential of creating energy or producing energy. I think of this as my 5-pound bag of sugar in my pantry, right? There's sugar. Now, if I take some of that sugar and I make a recipe, I make cookies or a cake with that sugar, and I consume it, what happens? My body takes that sugar and will break it down, and by breaking it down, do what? Release the energy. So the energy is stored within the sugar molecules, and it has the potential of being released in my body. The second kind of energy I want to describe is kinetic energy. Kinetic energy is the energy of movement. So when you're heating up that beaker of salt water and the molecules are moving as a result of that increased heat, that would be kinetic energy. And then the third energy would be activation energy. And activation energy, as it kind of alludes to, is the energy needed to activate something, to get something started. So every one of your chemical reactions in your body needs a certain amount of activation energy to turn it on, to turn the switch. So when you're starting your car, right, you've got to have something that's going to crank the motor. It's sort of like that idea. Activation energy is what's needed to start the chemical reaction. So in your body, you've got millions and millions, countless chemical reactions going on every second. Now, we can think about these chemical reactions being in your body. We can think of these chemical reactions as being your food spoiling in your refrigerator. It doesn't matter, right? There's chemical reactions going on as food spoils, as an example. So if you're thinking about chemical reactions, what can speed it up or what can slow it down? What can allow the rate of a chemical reaction to change? And I think the second one's probably the most obvious. Why do we put our milk in the refrigerator rather than keep it out on the counter? On the counter, it's going to last for a day or so, isn't it? Because what's going to happen? It's going to break down and spoil. Why is it going to spoil? Because it's warm. And what's in the milk? Bacteria, right? They're there. It's pasteurized, but there's still bacteria there. And those bacteria are going to, in a warmer temperature, do what? Start doing their thing and breaking down the milk and, quote, spoiling it. It's the same reason your vegetables, right? Your fruits, why do you put them in the fridge? To slow down the spoiling process. So we know that temperature increases chemical reactions. If you want chemicals to react faster, you warm them up. The second thing is concentration. How quickly will A and B combine to make C? Well, if I don't have very much A, or I don't have very much B, then I certainly can't expect much of a chemical reaction to occur. So the concentration, how much of something I have, is certainly going to indicate how quickly it'll do its chemical reaction. And finally, number 3 is the presence or absence of a catalyst. A catalyst is something that speeds up a chemical reaction, and enzymes are catalysts. So enzymes are biological catalysts. They are molecules in your body that speed up the reactions of your body. Without these enzymes, these reactions would not occur fast enough or at all to maintain life. So we need to have these enzymes. They have to be present. They have to be doing their job, or else we wouldn't have the reactions necessary to sustain life. And what these enzymes do, what catalysts do, is that they lower the activation energy. That is, they do what? They make it easier, right, for the reaction to occur. So catalysts and enzymes speed up reactions specifically by lowering the amount of energy needed to activate, to jumpstart, to get the chemical reaction to go. We've got about 5 more minutes. Let me get through enzymes, and then I'll introduce pH. So I'm going to get through the middle of the next page, and then we'll pick up with pH again on Thursday, and pH will also be a part of your lab next Wednesday for those who have lab next Wednesday. Now remember, some of you have lab Wednesday, some of you don't have lab until a week from Monday. Please don't wait. For those who have Monday lab, don't wait for 2 weekends to get started, because when you do get back from the holiday, we're going to have that test when? Right, that Tuesday, right, the second weekend, and I just don't want you to get caught. So make sure you start looking at lab 2, even if you don't have lab for another 10 days. So in this graph, what we're showing is that every chemical reaction is sort of like taking a boulder or a rock, and in order for the reaction to go, you've got to push that rock up a little bit of a hill. And then once it reaches the top of the hill, then that boulder will go on its own and roll down the hill. The amount of energy that you need to push that boulder up to get it over the top, to get it to go, is considered the activation energy. So in this cartoon representation, that upward slope, right, this upward slope represents the amount of energy that needs to be put into the system, into the reaction for it to go. So this upward slope represents the activation energy. You'll hear it called activation energy. You'll also hear it called the energy of activation. It's the same thing. So you might say EA, or you might see activation energy. So that's what this orange arrow represents, right? How high this little hill is. And what am I telling you that enzymes do? Enzymes make that hill smaller. So enzymes allow less energy to be needed. They lower or reduce the amount of activation energy for it to occur. Now, once that reaction gets to the top of the hill, it'll go, right? It'll go down the hill spontaneously and finish the reaction. But we have to get to the top of the hill. So looking at it in a different way, the blue line represents an uncatalyzed reaction. That is, the hill's a lot bigger, isn't it? It's going to take a lot more energy to push that little boulder up the hill to get it to the top so it can go. If there's an enzyme around, the hill becomes smaller. So in a graphical representation of an enzyme, the enzyme lowers the hump. It requires less energy for the reaction to go when the enzyme is there. Now, once you get to the top of the hill, right, either without or with an enzyme, notice that we get to the bottom of the hill in the same place. So we start in the same place, we end in the same place. The only difference here is that it takes less energy, less activation energy to get the chemical reaction to go. And that's what an enzyme does. We'll talk a little bit more about enzymes in the next chapter. You'll hear about enzymes, specific enzymes throughout the course, especially a lot more of them in second semester. So that's an introduction to enzymes. And I will definitely talk more about enzymes in chapter 3. Okay. Anything so far? I've got about 2 minutes. I want to introduce pH, but is there anything that I've said so far that just needs to be clarified? If there's any place where your mind was wandering, right, and you're like, oh man, I don't know what he just said, or you get home and it doesn't make sense, remember, in a few minutes I'm going to download this video. I will send and post the link to it, and I won't send an email or announcement, but under Blackboard, over on the side, it's going to say use YouTube video links. It'll be under Lecture 2 or Chapter 2. So last thing I want to introduce, so that you've heard about it as you start working on your lab things for next week, are acids and bases. Now, again, there are many, many ways of defining an acid or a base. If you've taken chemistry, you know that there's more than one way to describe an acid or a base. For this course, however, we're going to say that an acid is something that, when put into water, dissociates, right, separates into ions. And one of those ions will be hydrogen. So if you take an acid like HCl, hydrochloric acid, very strong acid, and I take this acid and I put some of it into water, it will dissociate, that is, break apart, and it will produce some H+ ions, hydrogen ions. If we get hydrogen ions out of this situation, we're going to say that's an acid. Conversely, if you take a base and you put it into water and it dissociates, it does not give you H+, it instead gives you what's called a hydroxyl ion, or an OH-. A salt, by definition, is something when you put it into water, it dissociates and gives you neither H+ or OH-. So sodium chloride is a salt, isn't it? And when we put sodium chloride in water, what did we get? Na+ and Cl-. We didn't get any H, we didn't get any OH-, so we're going to call that a salt. Okay. What happens when you put water into water? Anybody know? If I take if I take a beaker of water, right? There's water down here, and I put more water into it. Right? Water going into water. What's going to happen? Anything? I get more water. There will be a very small amount of that water that will itself dissociate. And when water dissociates, it's going to give us this H+ and OH-. It will break apart into an equal amount of H+ and OH-. That is, it'll be an equal amount of acid and an equal amount of base. And because water will dissociate equally into acid and base, we're going to say that water is neutral, right? And as we get into this pH scale, water, pure water, has a pH of 7, and we say that pH of 7 is neutral because it dissociates into an equal amount of acid and an equal amount of base. And this whole pH scale, I don't have enough time to tell the whole story, but this whole pH scale goes from 0 to 14, and things that are low pH, below 7, are acidic because they have more H+, and things that are put into water and give off OH- are basic, also called alkaline, and that drives the pH value above 7 as high as 14. So I'll pick up on the pH story, I'll pick up on the ion story, and we'll move through the rest of this chapter next Thursday. If you're having any issues with mastering, come on up and see me.